Hello everyone. Today we are going to continue talk about the Minesweeper game. In my last video, I talked about the steps that were involved in my rule-based AI for the Minesweeper game. I also explained how I solved the game using the simple rule, and I provided my pseudo code. Today we will talk about the advanced rules. A simple rule only consider one number tile at a time. In the advanced rule, we will be considering multiple number tiles at a time. If we are considering two tiles at a time, then I call it the linked pair rule. If we are considering three tiles at a time, then I call it the linked trial rule. This can be generalized to the linked group of n rule. I will explain the details about these rules later. Then there is what I call the ending rule. Ending rule is useful only towards the end of the game when the number of remaining explosive tiles becomes an additional constraint. Again, I will also talk about the ending rules details later. The simple rule, advanced rule, and the ending rule should cover all of the deterministic rules. When I say deterministic rules, I mean the logics that determine 100% whether a tile is explosive or not. On the contrary, there are also probabilistic rules, but I will just briefly touch on it at the end of the video. I will also talk about the pseudo code and estimate the winning rate with 30 games. So let's first talk about the linked pair rule. Linked pair rule makes the next move by considering two number tiles together. I have two examples here. In example 1, if we focus on tile number 3, we know that tile A, B, and C need to have two explosive tiles. But B and C cannot be both explosive because B and C are also next to tile number 1, which means B and C can only have one explosive tile. That leaves tile A no choice but to be an explosive tile. On the other hand, since B and C need to have one explosive, tile D cannot be an explosive tile anymore. Similarly, for example 2, tile B, C, D are next to tile number 2, which means they need to have two explosive. But tile B and C can only have one explosive because they are also next to tile number 1. This makes tile D an explosive tile and tile A non-explosive tile. So how can we solve this problem in a systematic way that is programmable? We can simply solve this problem by brute force. For example 1, there are a total of 4 unrevealed tiles that are next to this tile number 3 and tile number 1. Each of the 4 unrevealed tiles can be either an explosive or a non-explosive. This gives total of 16 possible combinations. I have listed all 16 of them here on this table. In this table, 0 is an assignment for a non-explosive tile, and 1 is an assignment for an explosive tile. Then we know that tile A, B, C must have two explosives. We can then mark combinations that do not qualify these criteria red. We also know that tile B, C, D must have one explosive tile. We can then mark combinations that do not qualify this criteria red. Combination 11 and combination 16 are the only two remain. In these two combinations, tile A is always an explosive and tile D is always a non-explosive. And that's how we are sure tile A and tile D can be solved. Following the similar logic, we can also solve example 2. Notice that there is a more elegant way to solve this problem without generating all possible combinations, but this brute force method is much easier to understand and to program, and this is how I implement it in my program. Now let's talk about what constitutes a linked pair. So a linked pair is defined as two numbered tiles that share at least one adjacent unrevealed tile. So in our example 1, tile number 3 and tile number 1 are linked pair because they share tile B and C. To summarize the linked pair rule, we first find all linked pairs on the map, and then we loop through each linked pair. For each linked pair, we find all of the pairs adjacent unrevealed tiles, generate all explosive non-explosive assignment combinations, remove conflicted combinations. In the remaining combinations, check to see if any tile is either always an explosive or a non-explosive tile. This concludes the linked pair rule. Now let's talk about the linked trial rule. Linked trial is very similar to the linked pair. The only difference is that it makes the next move by considering 3 numbered tiles together instead of 2. I have an example here. We will be focusing on number 4, 3, and 2 over here. We know that tile A and B must have one explosive because they are next to number 4, and number 4 already has 3 flags next to it. Similarly, tile D and E must have only one explosive because they are next to this number 2, and this number 2 already has a 1 flag next to it. But we also know that tile A, B, C, D, E together should have 3 explosive tiles, which means that tile C must be an explosive tile. Again, we can use the brute force method to generate all combinations, which I have it here. There will be a total of 32 combinations. Then we can mark all conflicted combinations red. In the remaining black combinations, tile C is always an explosive tile, and that's how we know that tile C can be solved. Linked trial is defined as 2 linked pairs that share a numbered tiles. So in our example, 4 and 3 are a linked pair, 3 and 2 are also a linked pair. The 2 linked pairs share tile number 3, which makes them a linked trial. The rules for linked trial is very similar to the linked pair, so I will just skip the explanation. Now this can be generalized to linked group of n. A linked group of n considering n numbered tiles at the same time. It is defined as the n-1 linked pairs with each pair sharing a numbered tile with at least one other pair in the group. The steps are all very similar, so I will also skip this as well. Now let's talk about the ending rule. Ending rule is used when, towards the end of the game, the remaining explosives become a constraint. So I have an example here. In this example, there are 5 unrevealed tiles on the map, A, B, C, D, and E, and there should only have 3 explosive tiles left. Using the brute force method again, we can lay out all 32 combinations. After removing the conflicted combinations, we are left with only 2, combination 11 and combination 22. Combination 11 will not work because combination 11 only has 2 explosive tiles. The only possible answer is then combination 22. Here is another example. We have 4 unrevealed tiles left on the map, and there should be 1 explosive. Using the brute force method and removing the conflicted combinations, we are left with combination 7, 8, 9, and 10. But only combination 9 has 1 explosive, so it is the correct answer. Notice that if the number of remaining explosive is 3 instead of 1, then combination 8 would be the correct answer. Okay, now we know how the ending rule is used. How can we use it systematically so that it is programmable? To explain the ending rule, I need to first define 2 types of the unrevealed tiles, namely isolated unrevealed tiles and non-isolated unrevealed tiles. Isolated unrevealed tiles are the ones that are not next to any numbered tile. If an unrevealed tile is not isolated, then it is non-isolated. So in this example, tile D is an isolated tile, while A, B, and C are non-isolated unrevealed tile. Okay, let's talk about the ending rule. Here are the steps for the ending rule. So first, we need to find all non-isolated unrevealed tiles on the map, and then we will need to generate all explosive, non-explosive assignment combinations, removing the conflicted combinations, and then in the remaining combinations, calculate each of their total number of explosive tiles. From these total numbers, we will extract their minimum and maximum. Right now, for me to explain the rules easier, I set the number of remaining explosive tile left on the map equals to A, and then I set number of isolated unrevealed tiles equals to B. So A would be the number that's shown on the top left corner of the game, and then B is simply the number of the isolated unrevealed tiles. We can represent those numbers on a one-dimensional scalar line. So for example, we will have a minimum that's represented by this red point over here, and then as we move to the right, the number will be increasing. So we will have maximum somewhere over here, but it has to be on the right side of the minimum. And then we will also have a red point that can be represented as the maximum plus B. Now depending on where our A is located, we can have different cases. So for example, case number 1 is when A is less than minimum or greater than maximum plus B. So this is an impossible case. A cannot be less than the minimum or greater than maximum plus B. If our A is somehow in these two regions, then something is wrong. In the second case, A is equal to the minimum. So if A is equal to the minimum, all isolated unrevealed tiles are non-explosive, and any combinations that has its number of explosive tiles greater than the minimum is a conflicted combination. The third case is when A equals to the maximum plus B. So if A is equal to the maximum plus B, all isolated unrevealed tiles are explosive, and any combination that has its number of explosive tiles less than the maximum is a conflicted combination. The most tricky part is case number 4. Case number 4 is when A is between the minimum and the maximum plus B. So if A is greater or equal to the minimum and less or equal to the maximum plus B, any combinations that has its number of explosive tiles greater than A is a conflicted combination. On the other hand, any combination that has its number of explosive tiles less than A minus B is also a conflicted combination. This case number 4 is actually a little bit tricky. The two ending examples that I provided above actually do not cover all of the scenarios in case number 4, but I think it's not that hard to figure out why this works. And then also, by the way, case number 2 and case number 3 are just special cases of case number 4. If you want me to explain more on case number 4, let me know in the comment section, and then I will do a separate video for that. Now let's talk about the pseudo code. The first step is to initialize the game by randomly click on an unrevealed tile. While the game is still in progress, we will be doing 3 nested while loops. It will be easier to understand if we start with the most inner section of these nested loops. First, we will play the game using the simple rule until it is out of move. Then we will play the game with the linked pair rule, again until it is out of move. However, during the linked pair playing, even if it makes just a single move, we want to go back to the simple rule and check the simple rule again, because that one linked pair move might unlock more simple rule moves. So the most inner two activities will keep looping until we are not making any more move by the linked pair move. Then we start to play the game using the linked trial move. Again, during the linked trial playing, even if it makes just a single move, we want to loop back to the inner section and see if we unlock any simple rule move or linked pair move. I stop at the linked trial rule, but this logic can continue to the linked group of n. I stop it at the linked trial because my intuition is telling me that Implementing the linking group of 4 and above will only provide incremental increase on the winning rate, but I could be wrong. I have never done the study. It might be an interesting project in my future videos, but for now I will stop at the linkage trial. Lastly is the ending game rule, because ending game rule is typically useful only toward the end of the game, so I have an extra condition to prevent the program unnecessarily executing the ending rule, which can be computationally expensive, and this extra condition is when the number of unrevealed tiles is less than 30. This condition has to be met before I implement any ending rule. The other while loop logics are very similar, so I will skip the explanation for the ending rule while loop logics. Finally, if we cannot make any move with all the rules that we mentioned above, then we will just randomly click on an unrevealed tile. This process continues until either we beat the game or we lose the game. Okay, this concludes everything I want to explain. Now we can jump into the demonstration and then see what's the winning rate after we implement this advanced rule and the ending rule. Finally, we have finished 30 games of Minesweeper, and this time we beat the game 7 times out of 30. That's about 23%. So if you recall, in my previous video, when we only implement the simple rule, the winning rate is only about 1%. Now it's 23%. This is a very big improvement. Okay, before I end this video, I want to briefly talk about the probabilistic rule. So I have a simple example here. Let's say we already start the game and I already randomly click 2 unrevealed tiles. One gives us number 2, another one gives us number 1. Now at the current stage, the rules that I explained earlier is pretty much useless because we don't have enough information to make our next decision. Therefore, we need to revert back to the random click action again. But depending on where you click on the map, the probability of steps onto an explosive tile is different. So for example, I convert the game window into a NumPy array, which is shown on the bottom. If you remember in my last video, the number convention that I use is I assign number 9 to an unrevealed tile, and I assign number 10 to an edge padding tile. So in the array down here, I also color coded the unrevealed tiles. Different color will have different probability of step onto an explosive tile. For example, in the blue tiles, because those 8 blue tiles are next to number 1, which means they can only have 1 explosive tile, the probability of step onto an explosive tile when we randomly click on the blue region is 1 divided by 8, which is 12.5%. Similarly, we can calculate the probability on the green region because the green region surrounds the number 2, which means the probability of step onto an explosive tile in the green region is 2 divided by 8, which is 25%. Similarly, we can calculate the probability in the yellow region, which is 20.78%. So ideally, we want to click where the probability is the lowest possible. So we should randomly click on the blue tiles first. Hopefully, once we click on that, it will expand the map further and then provide more information that can be used in the rules that we described before. So I didn't implement the probabilistic rule, but I feel that this is not going to be very difficult. Although I didn't implement it, I already have some idea. But I'm not going to implement this just for now because I really want to do the convolutional neural network. I want to see if I can train a convolutional neural network that learns the rules by itself without me coding all the rules. So that will be in my next video. If you like my video, please give me a thumbs up and subscribe. Thank you. I'll see you next time.